the sedimentation efficiency. And if you know, if you look at the diffusion term, so this is, next number where you have, size of the contaminant, size of the particle, velocity, everything is known. Boltzmann constant is of course known. Temperature, you can take the temperature where you are working. So, if you know the Peclet's number, then you can find out the diffusion efficiency, and your the total, eta value is, summation of this, and probably we are talking about 1 micron or less size particle. So you can take alpha equals to 1, which is the case in most of the cases. So you now know the value of, theta into alpha. So now you now know all these values. What are, now you can change your value of length of the filter or height of the filter, and can, find out what is the outlet concentration that you will have. So this is the phenomenal equation, comes from, typical, collector efficiency and phenomena. So there will be, some factor of safety should be there. So you can add a factor of safety and find out, what is the, length of the filter when you know the inlet concentration and outlet concentration. So you can find out the, design length of the filter. So that is how you can actually design a filter. And this particular diagram is nothing but, showing, how to find out transport efficiency to know the particle diameter when your particle diameter of the collector is 0.5 kilometers or 5. So this 500 micron particle is there for your series, for your as the sand particle that you are using. So I guess you can design a filter if we give a sort of, these values to you, right? So right, probably today, after today, we'll post the first tutorial where you can find, maybe some tutorials will be there, for finding out the length of the filter. Okay. Now we will talk about the hydraulics of the filter. We talked about the efficiency of the filter. Now we are going to talk about the hydraulics of a filter. You probably have learned about the hydraulics of a filter. You probably have been told about a formula, which you can use to, calculate the head loss through a filter. Okay. Now, I want to again give you a glimpse of, how these formulas are coming, because many of the times we just, try to remember or memorize the formulas without knowing, what are the physical implications or how they are coming. So let us consider that this is our filter bed, and length of our filter is, let's say, L. Okay, and maybe, let us say volume of the bed is V. Okay. Now basically this is, when you look at the flows here, the flow is basically, if you look at this is just a flow through a pipeline, and and this is almost like, the flows are taking place through the annular or through the channels that are created, between the particles. Okay, so they might be tortuous in nature, but they are basically, like the open, like some channels that are created. So it's basically hydraulic, flow of water through these channels. Okay. Now, if we try to find out, the flows, so normally the head loss formula is given by FL, pipe flow. For pipe flow, head loss formula is given by this 2 FL square by 2 GD, where so What is this d? D is not like the diameter, it's a, it's probably, you can write it as a hydraulic mean radius. So if you write hydraulic mean radius, which is for a pipe flow, so for a pipe flow, this is, pi d square by 4, which is the area, divided by p, which is pi d. So this is weighted perimeter. Weighted perimeter, sorry, uh, sorry, this is area divided by the weighted perimeter. So this is area divided by weighted perimeter, right? So the pipe is running full in this case. So we have the whole perimeter as the pipe, as will be applicable here. And we have pi d square by 4, which is the area through which the flow is taking place. So here you can see that this is d by 4, or we know that this is for a pipe flow running full. So this is the equation. So d equals to 4 over r 4 into rh. So we can write FL v square divided by 2g into 4 into rh, where rh is the radius of hydraulic mean radius, right? So that means, that gives me H equal to, or head loss, to this will be equal to FL square by 8G RH. Now, what is this RH? RH is now actually, as we have said, this is area of flow divided by, so this is for a pipe flow situation, right, where the pipe diameter is big. Now I'm just writing this for a general case. If RH is the hydraulic mean radius, then we can write it like this: area of flow divided by weighted perimeter. Okay, and so this is nothing but equals to, let me multiply with length over in the denominator and in the numerator. So we have weighted perimeter times length. All right, and so you see the area of flow into length. So what is the area of flow? The flow is taking place between the, if there are two particles like this, so flow is taking place through the area between these particles. So we what is this area between these two particles? This is nothing but the void, right? And if you multiply with length of the filter, so this gives us the total volume of void, right? So this is the total volume of void that we are talking about. All right, and now weighted perimeter over length. So what is the weighted perimeter for each particle? So this is the surface area of each particle. Okay, so we can say that for all the particles, over this whole length L, the weighted perimeter is nothing but, in weighted perimeter times length is nothing but equals to total surface area that is available. Okay, total surface area of all the particles. Okay, now let us see the void ratio is E equals to what, volume of void, sorry, the porosity E equals to volume of void divided by total volume. Okay, just ask me any state. If you don't understand, please you can stop me and ask me. Okay, so porosity is equals to this, and if you do 1 minus E, that's what we did in the morning. So this is nothing but total volume minus volume of void divided by total volume, right? So this is our, so this is nothing but volume of particles divided by total volume. Okay. All right, so let us write that um, total volume is nothing but the volume of bed, okay, and volume of particles, let us write volume of particles is as Vp, okay. Now, so you can see here the volume of bed is nothing but equals to, from this relationship, we can write this is equal to Vp divided by 1 minus, okay. So volume of void is then volume of void is nothing but equals to, so total equals to E times volume of bed, right? So volume of bed is like total volume. So volume of void equals to this. And so if you write this, this will become E times Vp divided by 1 minus, right? So this is Vp, Vv equals to Vp into 1 minus, you can write it like this. Okay. Now, so Vp is what? Vp is the total volume of all the particles. Total volume of all particles. Okay. And if you have, if you write small Vp as volume of each particle, okay, so then, and n is the total number of particles, okay, so then you can write that Vp, capital Vp equals to n into small v, right? Okay, so let us write here volume of void equals to E into n into small v p divided by 1 minus, okay. And so you can see RH equals to what? RH is volume of void, which is E into n into Vp. So this is volume of void, RH is equal to, okay, and divided by 1 minus E divided by, total surface area, which is, let us say n number of particles, and surface area of each particle is AP. So AP is the surface area of each particle. For this purpose, we are considering that all particles have the same size. Okay. So then we can write n is the number of particles and AP is the surface area of each particle. So the total surface area is n into 2. Alright. So it actually n cancels out, and what you get is E into 1 minus E into, you have small Vp by small a. Alright. So now you can see that things are lining up very nicely. And now, so what is the value of small Vp? If you consider spherical particle, so spherical particle, you can see that for spherical particles, AP by Vp is what? This is AP is equal to pi d square, which is the surface area, okay, and your Vp is nothing but pi d cubed by 6, okay. So this is, so your this is nothing but 6 by d. Okay. Now you can consider that so this should be the ideal case. Ideal case, when all the particles are spherical. So particles are perfectly spherical. So this is the case when we get this. But all the sine particles are never very spherical. So we have a factor which is called sphericity. Okay, sphericity, and if we include the sphericity, your term Vp by Ap, it becomes, so Ap by Vp becomes equal to, by psi d. Okay, so this is what we get by from Ap by Vp. Now, so look at that we have this formula here, HL equals to FMP square by 2GD, sorry, 8GRH. So you can write this as HL by L equals to F into V square by 8G into RH, right? Now you know the value of RH here. So if you plug in, let us try to plug in here. So you have F into V square divided by 8G, and in place of RH, what you are writing, E into 1 minus E, and your Vp by Ap is nothing but psi d by 6, right? And from this you can, so let me go into the next slide. Okay, before I go into the next slide, let us try to see how this, so velocity, velocity is, the velocity is nothing but your overall velocity. So this velocity is overall velocity, which is given by V equals to Q by A, right? Or let us write capital A, so which is the total cross section of our system. Okay, but if you consider that, so the area, actually the flow is not taking place throughout the cross sectional area. So if you look at the sectional area here, flow is not taking place through the cross sectional area, so it is taking place within the part of the area here. Okay, so what is the area through which so actual velocity is so let us actually, I'm little wrong. So this V is the actual velocity. Okay, and so overall velocity is the Vs is the overall velocity, which is the superficial velocity, which is Q by A. But what is actual velocity? Actual velocity is the velocity to the ports. As we understand, actually the velocity through the ports are much greater than your overall velocity. How much greater? Because we can write that I got that mixed up there. So Vs equals to E into V. All right. So this is what we get, for Vs, because E is the porosity, okay, and V is the actual velocity. So actual velocity, this is the, so these two should be equal. So that is how we, consider. And if we plug in this number, so what we get here, from here is that we get F into 1 minus E into UC from your V square. You write Vs square by, so V square equals to Vs square by E square. So if you write this, you'll see that we have Vs square and 8 and 6, they cancel out. Here you get V and you get 4 here. So you have 3 coming over, okay, and you have E square here, and you have E here, so it collects to E cube, all right, and you have 4, and you have G, okay, and you have psi times 2. So that is now the equation that you actually arrive at, when you so the equation that you get here is this equation, that head loss per unit length is equal to this. So let me write this equation again. So head loss per unit length of the filter is F into 1 minus E divided by E cube into 3 by 4 G into Vs square divided by psi d, or you can write EC or whatever diameter of particle. So here Vs is equals to Q by A, where Q is the flow rate through the filter, and A is the cross sectional area. All right, and you can understand, you can recall that this is equal to the same classical formula that we have known as like Karman-Kozeny formula that we have always been using for our purposes. Now there is more to this Karman-Kozeny formula. So this is for this is for the laminar flow. Now for turbulent flow, F dash is equals to 150 into 1 minus E by RE plus 1.75. So this is an empirical relationship that you will use. So we can actually replace this formula with this. H by L equals to F dash into 1 minus E by E cube. So F dash actually, so your F dash F dash is actually considering these factors as well. Let me write this here. So we can replace this formula as HL by L equals to F dash into 1 minus E divided by E cube into Vs square by psi d. Okay. Now 3 by 4 G has been incorporated into F dash. Now for turbulent flow, we get F dash equals to this. This is empirical relationship. So that means my HL by L is now becoming 150 into 1 minus E square divided by RE into 1 by E cube into Vs square by psi d plus 1.75 into F dash 1.75 F dash exactly 1.75 times 1 minus E by E cube into Vs square by psi d. Okay, and here what you get is you have this value. So here, so RE is the Reynolds number, and RE is given by the formula rho Vs into d, in place of d, write psi d divided by mu. Okay, so this is normally this is the formula, rho Vs d, let's say, divided by mu. So here we are replacing d by an equivalent of this d, as because we introduce the sphericity here. So if we introduce this, then this equation is becoming HL by L equals to by 150. So 150 into 1 minus square divided by RE is equal to rho Vs psi d divided by mu into 1 minus q into Vs square by psi d plus 1.75 1 minus q into Vs square psi d into g. Right? So we can write that HL by L equals to 150 mu into 1 minus e square. Okay, and we have rho g from here, rho g, and we have PQ. Okay, and we have Vs here and divided by psi d square, right, plus 1.75 to 1 minus e by q into Vs square by psi d into g. Okay, so this is our equation, and when so this is for this part actually comes for a turbulent flow, and this is for the laminar flow. Okay. Now, experimentally it has been seen that when RE is less than 6, you can neglect the second term, so that it becomes very small and you can neglect the second term. So this is then you can use this as HL by L equals to 150 mu into 1 minus e square rho g dq into Vs by psi d square. Okay, so this is what you see as your Karman-Korzeny equation, but this is this is for your clean filter. Understanding that there is no clogging has taken place in the filter. So this is when you have a clean filter and nothing is going through, and this is when you get this particular stuff. Okay. Now if you don't have, what happens over the time when you run this filter, obviously the head actually increases. Okay, so now if you try to draw a curve between the time and head loss through this head, you see that initially you have a head loss which is the clean filter head loss. Head loss, and so this is what you get from this formula, HL by L equals to this. Okay. Now, as you run this filter, the particles start accumulating. Okay, and then it actually rises like this. The heat loss rises over time, and so if you are driving the water, basically this is the available heat. You have to stop. The flow rate actually decreases, and you have to stop somewhere. When the heat loss is equal to the available heat. So then when there is a so this is the time we'll say, uh, let's say THL. So THL is the time when we have reached time for reaching, limiting rate loss. So beyond this, we won't have appreciable flow coming through the filter bed. Now, at this time, what we need to do is that we need to backwash the filter, as we have been knowing that backwashing cleans the filter. So, what you do, you have the filter and you have the particles deposited inside the bed. So, suppose these are the sand particles, and you have the contaminant particles which has got deposited within the bed, right? Let me choose a different color. So these are the contaminant particles which have deposited within the bed. Now, what we do is that you try to push, make the bed, the velocity is such that everything becomes in a suspension. Okay, so the weight of the filter is now not there, and we make this bed what is called fluidize this bed. We fluidize this bed so that there is no particles are not touching each other. Okay. So when this happens, obviously what happens is that the bed actually expands. The bed expands, and then the particles are the distance from one to another particle is increasing, so that there is no entrapment within this, because the particles are now far apart. The sand particles are now far apart. So all these small particles which have been settling, which have settled down, they try to escape with the water. So that is how you do the backwash. So after this backwashing is over, so all these particles will be going up like this. Okay. So after this backwash is over, you try to ram this again. So what happens when you fluidize this bed? So you create, the water passes through this, and there is a drag force which is created. So drag force is created, and when this is just fluidized, then drag force is actually equals to the effective weight. So that this is just like a suspended animation type of thing. So effective weight is now nothing but weight minus buoyancy. Okay. So weight minus buoyancy is your now. So, but after this, what happens is that we again pass the water in the cycle, and the water passes through this. But when you reintroduce the water, what happens is that initially, during a certain time period, some of the particles which are still there at the bottom, which could not get, its way, could not find its way all the way up into here, they cannot leave here. Okay. So initially, what happens when you re-enter the raw water, initially you get some bad water coming out of this. Okay. So this is called, so now if you try to draw a curve between, turbidity of product water versus the turbidity versus time. So what you get is initially you get a spike of turbidity here. Okay, and when these particles which are still at the bottom, they now will be washed out, right? So they will create extra turbidity, which you can see here. But when they wash out, the turbidity becomes very less, and what you get is, now you have a very, low turbidity, and when you reach the breakthrough point or maybe critical head loss, then the turbidity again rises. Okay, so this point when the turbidity rises, this is called a breakthrough. Breakthrough means probably breakthrough of the filter of the particles is taking place. Okay, and so but this amount of water you need to waste, right? Because this is highly turbid water. So basically, this is uh, water which is filtered water, but you actually have to waste this water. So we call it filtered to waste water, and and we have to stop this run here because then we have to go for a backwash. So this is actually your effective duration of filter run. So effective filter run is during this time. Okay, and this is called ripening time. So when you start your filter, then obviously some of the residual backwashed water and particles above, so they actually go, and then you have this ripening time. So you you have to stop, start draining this water for some time before you can start collecting. Okay, so this is what happens during the backwash. And if you look at the backwash hydraulics, so the backwash hydraulics, so let me talk about a little bit about backwash hydraulics. What happens during the backwash time? As I said, the particles are on, it's an incipient, they are actually at the level of incipient, fluidization. So we want to, so we said that the particles are there. So suppose we have this bed. Normally the bed is like this. This is, let's say, the length of the bed. Okay, and we try to backwash in such a way that the particles are just just starting to fluidize. So we call it incipient fluidization. So we call it incipient fluidization. Just fluidized, no extra velocity, nothing. It's just in an equilibrium. So at this time, so we can say the force of drag is equal to the effective weight of the particle. So this is what happens during incipient fluidization, and we actually provide water like this, and the bed actually expands. And let us call this expand bed is L. Okay, so it was L and becomes AB, and so how to find out the head loss in the expanded while in the expanded medium. So let us try to find out head loss in expanded medium. Okay, so as I said, the effective weight of the particle, so effective weight of the particles per unit volume of the expanded medium medium is how much? So effective weight of expanded media divided by the volume of media, right? We said per unit volume. So what is the effective weight? Simple. This is rho s minus rho into area is A, and we have L. Okay, so this is the effective weight of the media. And what is the volume of media here? So we have to also have G here. Okay, and if E is the porosity of the expanded bed. Okay, so that means we have you can see here, this is L divided by 1 minus EE, okay, and which you can write down as OS minus rho into G into 1 minus E, okay, and okay, so this is minus. Okay, so now if you equate this, effective weight equals to the so if you equate this, so you have rho s minus rho into G into 1 minus E equals to your force of drag per unit, so area into LE. Okay, so now so this is the force of drag and this is per unit volume, right? So if you now multiply, so now each side of the equation, equals to F3 force of drag divided by A. Okay, and what is this force of drag divided by A? This is nothing but equals to the head loss through the expanded medium, right? So this is nothing but rho G into H into LE. Okay, so this is in terms of head loss. Now that means and also what is the, so also we can say effective weight of the particles in, we have the same amount of particles here, so particles at rest in the filter at rest or in the normal situation, we are not changing the particle, okay, equals to the effective weight of the particles during evaporation, because they are effectively the same particles are there. Okay, so then we can write that rho s minus rho into G into 1 minus EE into NE equals to, I just wrote this side here, okay, and this side will be here. So this is rho s minus rho into G into 1 minus E. Okay, so this is 1 minus E is our particle uh, volume divided by the total volume, right? So then what you get here is that from this you can also find out that our rho g h a d, and if you look at this equation, you can find out that our h l e equals to rho s minus rho divided by rho into 1 minus EP into LE. Okay, and this is equal to rho s minus rho divided by rho into 1 minus E into L. So from this you can understand that if you look at the relationship between the expanded bed and the normal bed is nothing but equals to 1 minus E by 1 minus E. So this is the relationship between the expanded bed and the normal bed. All right. So now we want to know what is the backwash velocity. Let us try to go for this. If you need a break, I can give you a break for, let's say, 2-3 minutes or 5 minutes, and then okay, I can come back. Because I need to complete this thing today.
Excuse me, sir.
Yes.
Sir, can you please open to slide 12?
The slides are not open?
Sir, maximize size 12.
Maximize the slide. Okay. So then I have to. Okay, so I need to go for this. Is this okay?
Yes, sir, the next one.
Okay, next one. Oops. Next slide was just nothing. Sorry. The slide was just blank slide. I did not do anything. So this is the slide I was talking about. So next slide will be what I will be now working.
Slide number 12, please.
Slide number 12. This is the one.
Yes, sir. Thank you.
Okay. Have a look. All right. All right. So let us try to very quickly find out, what is the backwash velocity required when you design a filter, you have to also know the backwash velocity. We have seen, the backwash, what is the requirement of the backwash and what is the bed, height of the backwash becomes. So you have to provide an extra height, which is at least equal to LE. Otherwise, what will happen if your height is lower than this? The sand particles will escape from the filter, so which you do not want to have. And also, you need to provide some other freeboard so that you can contain all these particles inside your system. Okay. So if we think about backwashing, you know, so when we try to find out the minimum backwash velocity that will be required just for the bed to be just in the on the verge of fluidization. So we need the bed to be on the verge of fluidization, and this is the minimum backwash velocity that is required. So when we talk about, so this bed is not yet fluidized, but it is just on the verge of fluidization. Okay, so it is a fixed bed initially, and when we expand this bed, this is called a fluidized bed. So this is fluidized bed. But before this everything is fluidized, we just try to see the condition when it is just not a fixed bed, not it's just a fluidized bed, but it is still like, there are particles there that are sitting at their place. So and so we call it incipient, fluidization condition. And during this incipient fluidization condition, what happens is that it's still it is still, in this condition it is still uh, it is still a fixed bed. Okay, but so if it is a fixed bed, then we can say that HLE, that is divided by LE, that is the head loss across the bed, per unit length, when just the fluidization takes place or backwashing is done. So at this time we can also, it is a fixed bed, so we can actually write this equation, for this. So if we write this equation, this becomes 150 mu into 1 minus e square whole square, by, you have rho g here and you have v cube right there, and we call it, v minimum for fluidization, called VMF, and we have psi d square plus you have 1.75. We are, obviously this is a turbulent flow because we are talking about fluidizing the bed. So this will be v square mf by psi d into g. So if you look at with this formula, you see that we have included the whole formula right here. Okay, only thing is that we have changed the Vs with VMF, and this is it. Okay, but at this point of time, we are not done, because here we have this as effective equals to effective weight of the media. So this is nothing but, from here you can see, from this equation you can see HLE equals to rho s into rho 1 minus e into L. So we can actually write this condition here. So it becomes rho s minus rho divided by rho into 1 minus e, because the L term has got cancels because we have L divided by L. Okay, so this is what we get as an equation. So you can write this as 150 mu by, let's say we have d square here, we can write d square and we have 1 minus E divided by, let's say, psi square EQ, and we can have EMF right here. And also, you can see this is 1.75 into 1 minus E divided by EQ, and you can also collect these terms, rho by D, okay, and let me write psi here, okay, and then this is this BMF square, and the G has been, this G and G has been transferred over to this side, so you have rho s minus rho into G, right? So 1 minus E has been, from this side 1 minus E has been cancelled out, and also you can see that rho, rho which was at the bottom, so I missed a rho here. Oh, sorry. So here there was no rho, so we divided by rho here, and rho everywhere we divided by, multiplied with rho, so that here the rho is coming here and like this. So we are trying to find out an equation, and now what happens is that from experiments it has been found, it has been found that 1 minus E divided by psi square Q, equals to 11. So, don't ask me why this is like this, but this is what has been found out experimentally, that this is equal to 11, and we have 1 by psi into EQ equals to, it is 14. So this is the correlationship that they have found out for different sphericities of the particle and different porosities, and this happens during the minimum fluidization condition. So if you now plugging these numbers, what you get is that in this place you find 11, and in place of 1 by psi EQ you find 14. So that gives me 150 times 11, which is 1650, okay, divided by mu, and we have V square, okay, and we have VMF plus, we have now 24.5 rho by D VMF square equals to rho s minus rho H. So the equations are getting simpler, and now you can introduce this REMF, which is Reynolds number at this minimum fluidization condition, so which can be written as VMF rho into D divided by mu. So when you write this, what you get is that and you get this 24 right here, so we get 24.5, and you can see here rho D BMF, you use this BMF, so you can rearrange this equation and you can find out so let me rearrange this equation. Let me write rho VMF, just trying to manipulate this thing, by D divided by mu square, okay, plus 1650, okay, rho VMF into D by mu, okay. You can see this will become, now this side will become dq rho into rho s minus rho into g divided by mu square. So I'm just, multiplying everywhere by d cube rho by mu square. Okay, so d cube rho by mu square, and so that you can see this equation is becoming like 24.5. Now rho dmf by d by mu is REMF, okay, Reynolds number square, plus 1650 REMF, okay, minus you get d cube rho s minus rho into g divided by mu square. So this is equal to 0. Alright, so this is just the equation in a quadratic equation. Now you can now write GA equals to Galileo's number, and Galileo's number equals to d cube rho s minus rho into g divided by rho square. And with this we can write that this as 24.5 RE square plus 1650 REMF plus, sorry, this is minus, if you look at this equation, minus Galileo's number equal to 0. Okay, so when you have this, so you can now use the quadratic equation and solve it. REMF, I have done this and I have got it 33.7 square plus 0.41 GA to the power half minus 33.7. So this is what you get as your REMF. Now what we need to do, if you see this, we can find out from our particle size and everything the Galileo's number, because we know d, we know rho, we know rho s, we know rho, we know mu. So we can find out the Galileo's number, and when you find out the Galileo's number, you can find out the value of RE. So find out Galileo's number, and then use this equation to find out REMF. Okay, and when you know the value of REMF, so REMF is nothing but equals to rho DMF into d by mu. So in this, you know rho, you know d, you know mu, but the only thing is that you do not know VMF. So when you know REMF, you can find out VMF equals to mu REMF divided by rho d. Okay, so this is how you can find out the VMF. So design value. So this is the minimum velocity of fluidization. So design value is normally given as 1.35 times of VMF. Okay, so this is the backward velocity that we need to provide for this filter bed. So this is how we get this, and also when you find out this backwash velocity, what is the amount of flow rate that is required for the backwash is nothing but you have this BMF into 1.35. So this is your design. So your design value is 1.35 VMF, which is your backwash velocity, times your area of flow or cross sectional area. So this gives you the quantity of water or the flow rate, flow rate for backwash. Okay. So with this, I think you are in a position to find out everything for a filter. You know what will be the length of a filter, what will be the experiment length of a filter, what will be the amount of backwash water that you need to do. And today I don't want to linger further, but next time when we meet, we will try to solve this problem, and we try to find out the design of the filters, and using our our whatever we have learned. Okay. So this is what we get, and maybe next time we'll just find out the backwash velocity and net losses in this filter by this problem we will do. So today let me stop here. It has been a very long day for me. I have classes since the morning. um, so thanks for being with me for such a long time. uh, and at Friday, sorry, at this hour. So hope you have understood whatever we tried to convey. And if I will upload these slides immediately after this class. And if you have any question, you can ask me. So this is the problem that we will be doing in the next class. You can also start trying doing this. What we will do, we will try to solve this problem. We will try to find out a program or try to write a small program in Excel and try to solve this problem. you know you can see that there is a lot of calculations that are involved. So we will try to minimize this calculation by making a spreadsheet in Excel, which will help us to do this in a flash of a second, I would say. So let us we'll do this next time we meet. But you can try solving this problem, or try doing it on the Excel sheet as if you so wish. Okay. All right. Thank you very much, and I will see you on this Friday. So you can leave now.